Hello, we're going to go ahead and get started right away working through these problems. First one is find the distance between 2 points and then also find the midpoint. So first we're simply going to do distance formula, which is the square root of the x values minus the y values. You can go x values in any order, given you have 1 and then a negative. I'm going to do the negative second to make that positive, a little easier as far as the calculation. You want to go in the same order for the y's as you did for the x's, which really doesn't matter, but still I think it's a decent practice. So it's going to give us 4 squared, 1 plus 3 is 4, so 4 squared plus, it'd be negative 3 squared. Negative 3 squared is the same as 3 squared, so that'd be 16 plus 9 is root 25. Square root of 25 gives us a distance of 5. Now we want to do midpoint. So we can call it midpoint x comma y equals, and that's the average of the x values. So negative 3 plus 1 divided by 2, and then average of the y values, 8 plus 5 divided by 2. And that's going to give us a negative 2 divided by 2 is negative 1, and then 8 plus 5 is 13 divided by 2 gives us 6.5, or 13 over 2. That's supposed to be a little point there. Is a mistake on my part. Okay, coming down to, coming down to number 2, find the equation of the circle tangent to y equals at x equals 2 centered at the x-intercept of 3. This is one of those problems where you just try something. See if we can draw this out. Our first center is at the x-intercept of 3, 0. So I'm just going to go here. It says find the equation of the circle. So obviously here's the center of the circle. We need the radius. It's tangent to the line y equals x. I'm just going to draw the line y equals x. And again, this is just a sketch at the x value of 2. So I go, the x value of 2 is a vertical line at x equals 2, which means that this point is the point of tangency for whatever the circle is. Kind of using up my space for the other problem. But as we know with standard form of a circle, we want the center, which we already know is 3, 0. And then we want the radius, and the radius in this case, if we look here, is going to be that. Between those 2 points, we need to know the distance between those 2 points. Well, what is this point? The center is 3, 0. This point is where x equals 2 on the line y equals x. So we just go, if x equals 2, what does y equal? It has to equal the same thing, because it's the line y equals x. So if x equals 2, y equals 2. Now we go ahead and find the radius. So we go subtraction of x values, so 3 minus 2. Again, the order doesn't matter, because if I got negative 1 squared root, it would give us the same thing. And then 0 minus 2. And so that would give us a 1 squared plus a 4 squared would be a root 5. So now we write standard form, x minus 3 squared plus y minus 0. Same as this y squared. Radius is root 5 squared. Root 5 squared. The root and the square cancel, and we get 5. There's our final answer. Find the x and y intercepts of the graph. So first I'm going to find the x-intercept by plugging in 0 for y and just rewriting. So I have x and I have root 4 minus x squared. I look at that and I go, okay, how can I solve this equation? Well, I have 2 terms. So if you think of this as one term times 2 terms equals 0. Zero product property applies, meaning 2 things multiply equals 0 or more than 2 things. One of them has to be equal 0, so x is the first part that equals 0, and then the second part would be root 4 minus x squared equals 0. And now we just have an equation we want to solve. Square to get rid of the square root gives us 4 minus x squared. On the left-hand side, when we square 0, it is still 0. So I have 2 ways going about this now. Well, 3 ways actually. I could just solve for x. I could add over the x and square root. I could subtract over the 4 and divide by a negative. In either case, getting x by itself, or at least a squared term by itself, you get x squared equals 4. And then you square root, we get a plus or minus 2. So we have 0 and plus or minus 2. I kind of briefly described those two ways depending on what you decided to move over, the 4 or the negative x. The other way would be dots, difference of two squares, 4 minus x squared, to factor into 2 minus x and 2 plus x, set them equal to 0 and solve. Give you the same thing. Other way is finding the y-intercept. So we plug 0 in for x. I really don't have to write the rest of this out because 0 times anything is 0. So once again, we get a y-intercept of 0, which we got. It's the same y-intercept, x-intercept at 0 is 0, 0. Okay. Find the equation of a line with an x-intercept of 7 and a y-intercept of 0. So I'm just going to write out what info I have. I know my x-intercept is 7, 0, and I have the coordinate, which is a y-intercept, which is 0, negative 1. And so if I want to find the line, I need the slope and the y-intercept. Well, I already got the y-intercept as 0, negative 1. So now I got to find the slope. I could do 0 minus negative 1. I like that because that's going to turn it positive. So I chose on the y's what order I want to go in. But whatever order I go in for the y's, I have to go in the same order for the x's. And then it ends up working out nicely. I get a slope of 1/7. And so now I'm simply going to rewrite y equals 1/7 x and then minus 1 because I already have my y-intercept. Note, if that wasn't the y-intercept, then you just take either of the points, plug it into point slope form, and solve. Looking for symmetry. So first off, we're going to plug in negative x, and this is testing for the y-axis. So I'm going to plug in negative x. Now you may be able to, as I write this out, I'll go ahead and talk about strategy. You may be able to do this without looking, which is fine. If I do this, the terms that would stay the same would be that term and that term because of the squares. This term would change, so the whole equation does not stay the same, and therefore it's symmetrical. It's not symmetrical to the y-axis. Now I'm going to go ahead and plug in negative for y to test symmetry to the x-axis. I think it's, if you're understanding this concept, to determine symmetry, you'll see that if I plug negative y in for there, I think I need to write it out. If I plug negative y in for there, it's going to stay negative. It's not going to turn positive, so this is not the same. Now, if we plug negative x and negative y to determine if it's symmetrical to the origin, these terms would stay the same because they get squared. The negatives would get squared. Here, these two terms would change, and that's a problem because if I said, oh, well, I just got these two terms, they're going to cancel out. Well, we have this other term over here to consider. Furthermore, if we divide by negative 1, these would change these positive, but that would change those negatives. So there is no symmetry on this problem as it fails all three tests. Moving on to the next page, write the equation of lines parallel and perpendicular through that point. So when I see that, I want to think slopes. So if I have my equation of a line 5x minus 4y equals 8, I want to first solve, figure out what the slope of this line is. So and then I can work from there. So first off, if I solve, I get negative 5x plus 8. And then if you divide by negative 4, that would give us a slope of 5/4 x. And that would, 8 divided by negative 4 be minus 2. Y-intercept is kind of irrelevant in this problem, but nonetheless, I'm still working through it. So I know the slope of this line is 5/4. So if I want to first find a line parallel to it, which I'm just going to call M sub 2 lines for like that parallel notation symbol. Kind of looks like 11. That's not it. Really just can call it M if you want, but I'm just trying to indicate we're finding the parallel slope, which would be the same, which is 5/4. And then I have that point 3, negative 2. So I'm going to now plug this into point slope form because I have a point and a slope. And that's going to look like this, where I have the point 3, negative 2. The negative 2 goes in for y1. M is 5/4. And then I have x minus 3. And now I'm just going to go ahead and solve. So I turn that minus negative positive equals 5/4. I'm going diagonal here on the fraction just for space. Minus, and that would be 3 times 15, and that's still over 4, so I get 15/4. And now I'm going to have to subtract over the 2. Now when I subtract over the 2, I want that with the denominator of 4. Combine as efficiently as possible. Run out of room here, but I'm just going to go right here. Y equals 5/4 x. And now if I have negative 15 minus 8, I have negative 25 of those. So my parallel line that goes through the point 3, negative 2 is that right there. For perpendicular, doing the same thing, except I'm going to take that initial slope and I'm going to do the opposite reciprocal. So the perpendicular slope is flipping and making it opposite, be negative 4/5. And now we're going to go through the same process again. Y minus negative 2, I think I can write that as y plus 2 without losing any of you. And then I have negative 4/5, and I still have the x minus 3. I'm going to do the same thing. I'm going to distribute and then solve. So I have y plus, oh, actually I'm going to try to do this all in one fell swoop. So I'm keeping that minus 2 in my mind. I have negative 4 times negative 3 gives us a positive 12 over 5. And remember, I am subtracting, we are subtracting the 2, and I want a denominator of 5, so I'm just going to write the 5 right away. Why write the 2? Let's just write the 5 right away. It's a little more efficient in terms of writing it out. And now I have y equals negative 4/5 x, and I have 12 minus 10, which gives us 2/5, and that would be our final answer for the line that is perpendicular to that line and goes through the point 3, negative 2. Find a point P on the curve, y equals root x minus 4, such that the slope of the line through P is negative 1. How about we draw this? So at this point, we know that root x minus 4 will be a radical function at the point 4, 0, because Spider-Man rules has shifted it over. So I have that. And then I have point slope such that the point P, so some point on the line, I don't know exactly what point it is, it's generalized, it's x comma y. I can make my life easier by, instead of making it y, I know what y equals for every point in this curve. It's root x minus 4. So let's write that out. And then we have some 0.88 up here, and the slope between them is equal to 1. So if I do m equals y2 minus y1 over x2 minus x1, let's just plug in the information that we have. M is negative 1. We already know the slope is negative 1. y2 is either the 8 or the root x minus 4. So I'm going to go the root x minus 4 first. I think it's easier for me to work with. That's my y2. Minus y1 is minus 8. And I have x2 minus x1. So I have to go in the same order I went with the y. So I have an x here minus 8. And now I'm going to go ahead and try solving. So working through solving this. Give myself some room here. I really don't see anything other than multiplying by x minus 8. And so when I multiply by x minus 8 on both sides, it's going to look like this. I have x minus 8. Let's cancel. X minus 8 here. Note, put that in parentheses to notate that that's multiplication. And I'm distributing the negatives, so that'd be negative x plus 8. Might be nicer to write it with the 8 first. I'm just going to try to keep things as simple as possible here without trying to do too many steps at once, given this is an instruction video. And I want to solve for x. Getting kind of complicated here. Well, I don't like that radical, so I know if I get the I'm just kind of talking through my thinking here. I know I got that radical. If I get that by itself, if I get the root x minus 4 by itself, I can square it and get rid of the radical and then try to work with it from there. So let's just go ahead and do that. Let's see what happens. So I have negative x. I have to add over the 8 from the right-hand side. So 8 plus 8 gives you 16. And then you have this root x minus 4. And I go, I do not like that root, so I'm going to square it. I need to square this over here. And when I square this on the left-hand side, which I'm going to bring that over here, x minus 4 equals, square that side, it's negative x times negative x is x squared, and then I have two negative 16x's, so that'd be a negative 32x. I'm just foiling, distributing, and then I have a plus 256, which is the 16 times 16. And now I have a quadratic. I want to get a quadratic set equal to 0, so I'm going to go 0 here. I have x squared. I'm going to move over the x, will give us a minus 33x, and then I'm going to add over the 4, which gives us a 260. Now we're going to have a factoring challenge here. This is a relatively somewhat challenging factoring. I got 13 and 20, and I want those both to be negative. I don't think you're going to have that bad of factoring on the test. I think you'll be fine if you know your basic factors, and you'll be able to find it. So let's see. 13 times 20. Both of those have to be negative. Negative, negative multiplies to be 260, and then add them together gives you negative 33. And that's going to give us a solution of x equals 13. 13. 13 and 20. Let's go back to what we're looking at here. Find a point P on the curve. So we got x equals 13. Well, now we got 2 points, 13 and 30. So I think we do 13, and then we got to plug it into that root x minus 4. So I plug 13 in. You can look at it right here. If I plug to get the y value, I'm going to plug 13 in for there. Root 9 gives us 3, so we got that point. And the other one would be 20. And if I plug 20, look at this, nice and neat. If I plug 20 in for here, 20 minus 4 is 16. Root 16 equals 4. So those are the points P that would have us on that curve that has a slope of -1. Okay, so now we're going to look at the difference quotient, which I think we have gotten a good amount of practice on. This is nothing more than a complicated or relatively challenging version of doing substitution and then simplifying, which could involve factoring, combining like terms, and so on. So first off, before we find the difference quotient of f of x plus h minus f of x all over h, just right here, we already know what f of x equals, so we know what to substitute in for that. That's this right here. We need to know what f of x plus h is. So I'm going to write out what f of x plus h is. And my suggestion, before you try writing it out, I suggest just writing it out with the x's having open parentheses. And then we can work on, okay, what goes in for, well, what if this was like f of 2, then 2 would go in for here. If this was -5, then -5 would go in for here. Well, this is now x plus h, so that's what's going in for here. We have x plus h, and now we have the difference quotient to write out, where we have f of x plus h minus f of x. I'm going to write the first part in parentheses, or brackets, because I know they have parentheses. So this is f of x plus h, which is right here, and f of x plus h equals all this jazz. So I'm literally just taking this and inserting it for the variable. So what will that look like? Again, just rewriting it. Didn't get myself, I think I can get it in. It's going to be close, and not bad. It's supposed to be a -1 there. There we go. Okay, and now we have the f of x, because this is f of x right here, and that's what we have, f of x, so that goes in. This is the substitution, the challenging form, relatively challenging form of substitution. Now that we have all the substitution done, we are simply simplifying. We're going to do some distributive, combine like terms. So first off right here is x plus h times x plus h. We've done that multiplication multiple times. That'd be x times x, and then x times h, plus hx, which is the same as xh. And then h times h is h squared. So that would be x squared plus 2xh plus h squared. I'd suggest doing that by hand. If you have challenges in your course, you can ask your teacher on that. But we also have the 2 out front. So we're going to multiply that by 2 as well. So we have 2x squared plus, remember the middle term was 2xh, and we're multiplying it by 2, so that's 4xh, plus the last term is h squared, which was multiplied by 2, which is 2h squared. Then we have a plus 3x, distribute the 3 in, so we have a 3x plus 3h. Then we have the -1. This is all that first parenthesis, minus the f of x. I'm not doing anything to this. I'm just going to rewrite 2x squared. So I'll make sure I got this right. Plus 3x, okay? So plus 3x and then -1. That's all over h. Okay, so first off, distributing, so all these are negatives. I don't think we need to rewrite. I think we can see the canceling of terms. So we have like terms, we have 2x squared with a negative 2x squared, so that goes to 0. We have a 3x with a minus 3x, right, because the negatives, and then -1 minus -1, those all go away. So now we have, it's all divided by h. We have a 4xh left over. I'm going to erase this and try to. Here we go. Let's make it a little smaller and out of the way of this next line. I'm getting some glitches here. Here we go. Okay, 4xh plus 2h squared plus 3h. And when you get to this step, all the terms should have an h in them. Now that's not 100% check to make sure that you did it right, but that's a reasonable check to make sure that you're on the right track here. So we can cancel out h's from all of them, or you could look at it as factoring out an h in the numerator. And then when you factor out an h in the numerator, we're all in terms of multiplication. It's a very, very poor line there. So we factor out an h, we have a 4x plus 2h plus 3, all divided by h, and the h's cancel. And then you could rewrite that or just box it in. That's your final answer. Find the domain and range of the following. So, domain, you will have to find or be able to find domain and range graphically and algebraically. So we will work through that. On the first one, A here, if I want to find the domain algebraically, I know that the restrictions on this function is that the denominator can't equal 0. So I'm going to set the denominator equal 0. I'm not going to write it as not equal to 0 to confuse myself. I'm just going to write it as equal to 0 and keep in my mind that this is the restrictions on it. So if I factor that quadratic, what multiplies me negative 6 and adds me negative 1, that'd be negative 1 and positive 3, and therefore we have the 3 and negative 2 would be the restrictions on that. So therefore the domain of the first one would be negative infinity to negative 2 union, it's all in one line, negative 2 to 3, union 3 to infinity. Now on this one, finding the domain or the range of this algebraically is kind of not straightforward in terms of the algebra. I don't want to go too deep into the mechanics and characteristics of a rational function, but what I would say is that we know that, long story short, if you don't have a whole or anything canceling, what you want to do is look for what is the restrictions on your outputs. Well, the restrictions on an output for a rational function like we have here is we have vertical and horizontal asymptotes for a rational function. When we have a horizontal asymptote, what we want to do is look at what that horizontal asymptote is, and that's your potential restriction. Well, we know that as a function goes out to infinity, a rational function goes out to infinity, that is what your restriction is on the range. Okay, so let me draw something really quick. Like if here is function goes like this, as x goes to infinity, the outputs are going to approach the horizontal asymptote. So for this one, we look at what's going to happen as far as when x goes to infinity, the denominator is going to get way, way bigger than the numerator because it's a squared. So if I think about it, if you have like a billion in the numerator and you square a billion, it's going to be way, way bigger. And remember, we're going off to infinity. So a billion's a relatively small number compared to infinity. You know, you go a quintillion and so on. Anyways, we know that we're approaching 0 because the denominator would get extremely large relative to the numerator, which means 0 should be our restriction. Well, you could just check it, and if I plug 0 in for here, we would get 0 over 0 and a 0 and a negative 6, which gives us a y value of 0, which indicates that we actually do have an output there. So therefore our range, the one spot where we would have a potential restriction on the y, we don't, and therefore the range would be negative infinity to positive infinity. For b, we're going to do the same thing. Note on b, for you got a little more going on in the numerator there, but it's not like a square root function or anything else that would give a restriction on the inputs. So the only restriction would be the denominator set equal to 0, which would give us x equals 2. So our domain is going to be all values except for 2. In interval notation, we write it like this. Now, the interesting part about finding the range algebraically is I am going to factor the numerator and see what happens. So if I factor the numerator, we can talk more about this in class, of course. If I have negative 14 and it adds to be 5, that would be a positive 7 and a minus 2, and then divided by x minus 2. And so now what we see is the x minus 2's cancel. So our function is simplified to be f of x equals x plus 7. What that means is graphically, we're really just graphing the line x plus 7 with a hole at the x value of 2. So we know that there's a hole at the x value of 2, but we need to know what that output is. Well, now that we have it simplified, we can take that 2 and insert it into here. If we take the 2 and insert it into there, 2 plus 7 is 9. So 9 is not an output because 2 does not produce an output, and therefore 9 is your restriction. So therefore I'm going to write it up here. Range would be negative infinity to 9, union 9 to infinity. And any sort of graphing on domain and range we potentially look at later. Okay, for 10 here, we're just plugging in negative 3 and simplifying. Negative 3 here in the numerator. Denominator, excuse me, I have negative 3 squared minus negative 3 minus 6. Let's give us negative 3 in the numerator. I have a 9 plus 3 is 12, minus 6 is 3, which reduces then to negative a half. B looks a little daunting, but if you kind of visually break it down, it's really not that bad. It's just f of x is in solve for. So you go, okay, I'm going to solve for f of x. So if we solve for f of x, we get, let's see, the x's cancel. And I have 5 plus 13 is 18. And I subtract over the 8, that gives us 10. So that's a constant function. It's not supposed to be an equal sign there. So it doesn't even matter what our input is, our output is always 10. For C, we have not done those. Those are step functions. We have not done those. So moving on. Okay, we're not doing height of a rectangle, but we are doing the average rate of change of a function. So if we recall from a graph, average rate of change between 2 points. So let's say I have some curve here, and I want to find at the x value of 1 and x value of 4, what's the average rate of change? That's the secant line, which goes through those 2 points. And so we do y2 minus y1 over x2 minus x1. Well, how do we find that y2 and y1? Well, we're just going to plug 1 in for x here, get an output, plug 4 in for x, get an output, and then we have a coordinate 1 comma whatever and 4 comma whatever. Okay, so there's different ways you could go about it. You could simply plug in the 1, get the output, and then just go and write the function. Same with 4, and then you just have numbers in that y2 minus y1 or x2 minus x1, or you could literally write it out with this, with 1 and 4 plugged in within the slope intercept. I'm simply going to do it this way, where I'm going to write what is f of 1. F of 1 is, and this is plugging 1 in, so I have 8 divided by 1 plus 1 squared. So f of 1 is, let's see, it'd be 3 minus 8, negative 5. And then f of 4 is going to be 2 minus 8 divided by 4 plus 4 squared. That would be 2 minus 2 is 0, plus 4 is 16. So I have 2 coordinates, 1 negative 5 and 4 16. So we go m equals 16 minus negative 5. And note, I don't think I made any mistakes on this, but I could have small calculation errors, so I apologize in advance if I did, but I'm pretty sure I got all these numbers right. So I got m equals m equals minus negative 5 is 21, over 4 minus 3 is 3, and then that would be a slope of 7, so that would be our final answer, average rate of change. Okay, next we have a piecewise function. My suggestion is to do an input-output table because that eliminates the need to have to get creative with any of like our models. Like a linear model is usually like y equals mx plus b, or for instance the last function you see is negative root x plus 6 plus 6 plus 6. If you try to use like Spider-Man rules, transformation rules, may work, but the problem is it only gets graphed from 3 to 10, so you might I think it's just easier just to pick reasonable, correct inputs, get a reasonable graph, connect, and do that for all 4 parts. So what does that mean? Meaning, if we're just graphing this function from x less than negative 3, I'm just going to take and I'm going to plug in maybe 2 or 3 values. And I know there's a line, so I really only need 2. But I could do more if I want. I'm going to take negative 3 and insert it, get an output, get a point. Then I know it's less than negative 3. So I'm going to go to like negative 4, negative 5, get those points, graph it, and then move on to the next section. So first off, I'm going to write here x and f of x, just so we have a note of our coordinates. Negative 3 here, if I insert negative 3, minus negative 3 is positive 3, 3 minus 5 is negative 2. And note, I'll also show you a way of when you graph, instead of just like, here we're just like plugging and chugging and then graphing. There's not much thought other than the calculation. But after we can get done, we can kind of take a step back and then look at it and go, oh, does that match up with what I know about a line, a quadratic, and so on as far as the graph? Does that seem reasonable? So first off, negative 3, then I'm going to go negative 4. So negative 4 is going into this part, minus negative 4 is positive 4, 4 minus 5 is negative 1. So I'm going to graph those negative 3, negative 2, be not right there. Fallible Mr. Fossey, let's try that again. Negative 3, 2 would be right about there. And then I have negative 4, negative 1 would be right about there. Now the one thing I do have to be careful with is that x greater than negative 3. So at 3, negative 2, we should have a hole because of this being less than and not less than or equal to. So if I continue that, I can do one more value if I want. If I plugged in negative 5, I put that in here, opposite of negative 5 is positive 5, 5 minus 5 is 0. I put that here, and now it looks like I got a line, looks something like that. And now what I can do is look at this and go, okay, my slope's negative 1, so do I have a slope of negative 1? Down 1, over 1, down 1, over 1, yes. My y-intercept's negative 5, so if I can continue this, down 1, over 1, down 1, over 1, down 1, over 1, do I get a y-intercept of negative 5? 1, 2, 3, 4, 5, yes I do, so that looks good. Okay, now I'm going to come to this next part, plug in negative 3 in for here. I do it in a different color, so put a star there, maybe put a star there, indicate the different colors. So if I plug in negative 3 in for here, negative 3 squared give us 9. We still have that negative out front. So negative goes in for here, the negative with this negative right here gets squared, but we have the negative out front. So we have negative 3 squared is 9, the negative out front, so it'd be negative 9. Negative 9 plus 4 is negative 5. I'm going to go with 0. Maybe I want to do more than negative 3, 0, and 1. I may want to do negative 1 and 2. But for right now, I'm just going to go 0 because 0 is easy to calculate. And I'm also going to have to do 1 because that's the critical point or the key point when you're switching from one part of the piecewise to the next. So let's just go with 0 for now and see if that helps us along with the 1. So if I plug in 0, I get a 4 out. Plug in 0, I get a positive 4. So let's graph those 2 points. Oh, how about I'm going to do the 1. And then we'll go ahead and graph. If I plug 1 in, I get 1 squared, which is 1. But I have that negative out front. So I have negative 1 plus 4 is 3. And that's going to be an open circle. So first off, let's graph negative 3, negative 5, negative 3, 1, 2, 3, 4, 5, and that's a closed circle at -3, -5. 0, 4, 0, 1, 2, 3, 4, and then 1, 3 is an open circle. Now it's kind of hard to determine what am I doing there? What does that look like? Well, if I look at this, now I go to, well, I know about my transformation rules. First, my parent function is a quadratic, so it's a parabola. It got flipped upside down, so instead of facing like this, it's facing down. And this now has been moved up 4 units, the +4. So that would make sense that my graph would look like this. Now, again, I could get the 1 and the 2 again if I wanted to, but I feel comfortable with what I have there, and there is my graph so far. Then I know from 1 to 3, we just have an output of 3. So right here, I don't even have to do an input-output table. I know for 1, which is a closed circle, is the coordinate 1, 3. It just happens to be at that same point. All the way up to 3, x value of 3, that's a closed circle, and I have a horizontal line. Okay, next I have this last part here. And I'm just going to over here. So I have an x value of 3. So if I plug 3 in for there, 3 plus 6 is 9, square root of 9 is 3. That works out nice so far. So I got a -3 plus 6 is 3. So I got a 9 out inside the radical. That's nice because that's a perfect square, right? Square root of 9. So I plugged in 3, I got 9 out. The next one, that would be really nice if I kept these whole numbers. If you don't, that's fine. You can plug in 4, you can plug in 5, or you get decimals, and then you just graph it, and then just estimate. But I'm going to try to make this 16. If I try to make this 16, I would need an x to be 10. So I'm going to pick an x value of 10. If I pick an x value of 10, plug in the 10, I get 10 plus 6 is 16, square root of 16 is 4, I have a -4. So -4 plus 6 gives us a +2. Now I'm going to graph that point. 3, 3, so 3, 3. Again, happens to be that same point that ended with the blue. And then I have a 10, 2, 10, 2. Now, it might be wise if I found another point within there. So, for instance, if I did 4, that would give us like root 10. So if I did 4 here, I get a square root of 10. A square root of 10 is like, a little bigger than 3, like a 3.1. So I have like a 3.1 here. And again, like 3.1, 3.3 really doesn't matter when we're talking about estimates as far as graphing. Right, so like different y values, like if you have 0.1 versus 0.3, it doesn't make much of a difference. So I'm just going to estimate here. If I plug a 4 in for here, root 10 is 3.1, and I have 6 minus 3.1, gives us about 2.9. So let's see what we get here. 4, 2.9, and that makes sense. It's starting to go down more. So we kind of have this curve going like this, kind of hard to graph, but it should end at that point. Probably has a little more of a curve to it like that. Okay, so for that graph, here's our chance to practice domain and range graphically. So first off, the domain. What do I do to find domain? Take a vertical line. I'm going to move it left to right. You can see what inputs give us outputs. This is going off to -infinity, so -infinity over, we have outputs until we get to this point, but we do have an output there, so I don't see any breaks in the graph. Unless I did something incorrect, we have no holes so far in the domain. All inputs give us outputs. And here, where we did have a hole, we have a point there, and same here. So I don't see us having any restrictions on the domain. So it would be -infinity to infinity. And I do want to check, let's see, make sure I agree on the 1 over here, coming back to here. If I plug 1 in, 4 minus 3 gives us 3. Yeah, so we do have the correct output. Yeah. Okay. Sorry, I was rechecking my work on my key. Okay. Range, do the same thing as we did for domain, except we are going down to up. So our first output is right there, which is a -5. So we have bracket -5 because it includes it. And it doesn't look like I see any breaks in the, I mean, we don't have an output there, but we do on the red part. So there's no breaks there, no breaks, no breaks, and that goes all the way up. This is going to continue up to infinity. Maximum values are relative maxes. Since right here we don't have an output, it really doesn't count. That would be our maximum, relative maximum right there. So I'm just going to put max value. I'm going to go relative max value would be 4, but actual max value would be infinity because we are going up to infinity. Min value, we only have 1, doesn't go down to negative infinity. It would be right here. It should stop at, what's that, -5. Next, intervals, where the graph is increasing, decreasing, constant. This is my suggestion. You start off right increasing, right decreasing, you write constant. You start from the left-hand side and move to the right. It's decreasing, decreasing, decreasing until we get to that point. So negative infinity up to the x value of, what was that again, 3, -3. So we're decreasing from negative infinity to -3. And no for increasing, decreasing, constant. You're always using parentheses. Then as we continue to move this way, as I move left to right, from here to here, the y values are going up until there. So that'd be an increasing interval from -3 to 0. The graph from here to here is a constant function. So it'd be constant from 1 to 3. I did skip over, my apologies. When I went to here, I stopped right there, but we have it decreasing from there to there. So the decreasing will go from 0 to 1. And then lastly, this graph is definitely going down, so we're decreasing from 3 to 10. So again, I suggest going from left to right. No skipping, even though I did. I've been quite proficient, I think, at these, so my suggestion is definitely not trying to find all the increasing, then finding all the decreasing, then finding all the constant. My suggestion is going from left to right and fill in your increasing, decreasing, constant intervals accordingly. Okay, so next page, given the parent function, describe the following transformations. So if we have the +7 on the inside, that would be left 7, Spider-Man rolls. Inside, Spider-Man's not happy. You ask him to move +7. He's not going to listen to you. He's going to move -7. And that's transformation on the X, so that's left-right movement. -5, asking Spider-Man to move -5 on the outside. He is happy, so he listens, and therefore I'm just going to write U5, meaning we go up 5. For B, we have a -4, so that would be a right 5, and then we have a minus on the outside, and I'm just going to use this graph. Minus on the outside meaning that any positive outputs for the function are now going to be negative, and vice versa, negative, positive. So we have this type of movement from up to down, which means it's a reflection about the x-axis. And I like thinking of it as the movement, because then when we have a negative on the outside, we think up-down change. And if you think about that up-down movement from top to bottom, it then tells you you're reflecting over the x-axis. Rather than trying to remember a reflection on the outside, reflects over the x-axis. That intuitively doesn't make sense to think of outside outputs x-axis, but it does if you think about the movement from up to down or down to up. Okay, so C, we got those negatives in there. So how about we factor out a negative and see what happens? So I factor out a negative, but that negative still needs to be squared, right? Because this negative is within here. So when I factor out a negative, it's before this parenthesis. This parenthesis turns into that exponent. These two terms turn positive when we have a negative out front. That's a -1, and that -1's quantity squared, which turns positive. So really this simplifies to be x plus 1 squared, which is just a movement to the left 1. Given the graph, do the following transformations. I would suggest writing out these coordinates, perhaps 1, 1. This one right here looks like 1, -3. And then this one right here looks like, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, -3. So, things that we are doing. Negative on the outside has to happen first, then the -4. So first off, this gets reflected over the x-axis, down 1, and then we have to move down 4. 1, 2, 3, 4. So I'm starting at 1, 1, and I'm getting reflected to there, and then I'm going down 4. 1, 2, 3, 4. 1, 2, 3. Right there. Here we're reflecting about, again, the x-axis, so up 3 and then up 3 again, 1, 2, 3, but then we're moving down 4, 1, 2, 3, 4. So I'll demonstrate that again, starting here. We're reflecting up 3 and then down to here, which puts us right there. And the next one would be at, I know that would be horizontal with an output of the same as that last point. And now, how do we connect these? I think it's pretty straightforward that we connect them like that, but if you get a graph that's a little more complicated, like if you get some sort of V, it might be a little harder to determine how to. So what I do is I just like look at, like, okay, if I took this and I flipped it and then moved it down, how would I connect them? I'd connect them like this. So for B, now we're just taking each of these points, moving them over to the right 2, and then up 5. So if I start at 1, 1, start at 1, oh my goodness, 1, -1. No, -1, 1. -1, 1. I did all those transformations right, I just wrote it wrong. I felt like someone was off on that. Okay, so coming back over here, so I'm starting at -1, 1. -1, 1, I'm going to move to the right 2, 1, 2, and then up 5, 1, 2, 3, 4, 5, so that gives us a coordinate 1, 6, 1, 2, 3, 4, 5, 6, and then 1, -3 is my next point. I'm starting at 1, -3, so I'm going to move over 2, and then up 5, 1, 2, 3, and then 4, 5. I think I got that right. And then you move this over 2 and then up 5, so something like that. There we go. I think I got those right. Okay. Next we're doing some composite functions. It's the same. We're finding f of -3 and then finding -3, plugging in for f, and then whatever that gives us an output, we plug that in for h. So first off, f of -3. Plug -3 in for there, and -3 in for there. So -3 in for there would be -15 minus 2 is -17 over -10, so that'd be 17 over 10. And then we're plugging that in for h, so 17 over 10 squared plus 2. So if I simplify that, you just use your calculator for that, that'll give you 489 over 100, or you could put it in decimal form, would it give us like 4.89-ish? Yeah. Okay, so k of x plugged into g. So I'm just going to put the equal sign here in the interest space. I first write out g, because that's the outside function that's being plugged into. That plus 2, that's our g function, 3/2 x plus 2. And then we're plugging k in for it, which would give us a root x minus 4. Let's go ahead and distribute. So it gives us a 3/2 root x, and we get a minus 6, because that would be -12 over 2, so minus 6 plus 2, and then I could replace that with a minus 4. Just trying to keep the space nice and compact, efficient with my work. Okay, so h followed by h. What does that mean? That means we're taking the function and we're inserting itself into it. That may seem, we did that before, it may seem relatively challenging, so we can always fall back on our crutch. Our crutch is writing the outside function. The first one, even though both of them are h, it's important that we think of the first one being written on the outside, x squared plus 2, x squared plus 2. And now we are inserting h in for that. H is x squared plus 2, so we're going to insert x squared plus 2. And now we're going to, so let's go ahead and FOIL or multiply that out. So x squared times x squared would give us x to the 4th plus our middle terms would be 2x squared. There'd be 2 of them. So 2x squared plus 2x squared gives us 4x squared plus 2 squared, which is 4. And then we have that plus 2 in the outside. And just in the interest of space, I'm going to just write in the line below, or you could have combined it all at once. I'm going to do 4 plus 2, which gives us 6. All right. So next, we have all these different functions and we want to express them as some composition of m, n, and p. So I look at this and I think it's hopefully easiest to recognize the outside function as a square root. So I'm going to want that n on the outside. So I'm going to put an n here and I figure out which ones would I want to plug in order to get x cubed minus 3. So this is kind of like a puzzle piece that you're putting together. It's no real set procedure. Well, I do see that if I have m is x minus 3, if I take that p and insert in for there, I get x cubed minus 3, and then that gets plugged into the n, would give us this. So I want to plug that p in for the m. So if I want to plug the p in for the m, p is my last one. And so p gets plugged into m, which m gets plugged into n. I have 3 parentheses, so I'm just going to go 1, 2, 3, and I'm done. The next one is x minus 6. So this may be like, I don't know. Well, let's just try, for instance, like process of elimination. Could I use n? Well, there's no square roots in there, so probably not a good idea. I mean, I guess if you had another function that had a squared in it, then maybe you could, because the square and the square root may then cancel out. Doesn't look like it here. X cubed. I don't have any x cubed here. So, well, what could I do then? Well, I have m, and I could just give it a try. Just plug m in for m and see what would happen. If I had, in note, I'm just going to do x minus 3, right? If I plugged x minus 3 in for itself, oh, look at the minus 3, and the minus 3 turns to a minus 6. So that gives us exactly what we want. Okay, next we are looking at using these two graphs to find out what f of g of 6 is. So what does, I'm just writing in lowercase, not that it matters, f of g of 6. Well, this means we're going to take 6 and plug it into g. That's the input of 6. We get an output. That output now becomes the input of f, and then we find the output for that. So first we're going to take 6 and plug it in for g. So if I go over here and I look for 1, 2, 3, 4, 5, 6, I go up and yeah, that's supposed to be 1. So g of 6 equals 1. So I'm literally going to replace g of 6 with 1. And now we see that 1 is now the input for f. So I come over here and I go the input of 1, and they go up, and it looks like we're somewhere between, like that looks like 2 and that looks like a 3, so I'm somewhere between. So I'm going to say like about 2.3. And if I think on the test it's all whole numbers, so you're on a graph you're not going to have to guess. So about 2.3. All right, 20. We are finding the inverse of h. So there's 2 ways we could do that. First way is we just replace h of x with y, and then we interchange the x and y. And now we're going to solve for y. Let's see if I can do this in one fell swoop. First, I'm going to move y to the left-hand side. You can think about that being the last step. So to solve for y, I would add 3 to x first. So I have x, I'm going to add 3. And then I'm going to multiply by 2, right, because I have a half y, which ends up giving us 2x plus 6. And then we are going to get rid of the y and replace it with h inverse of x. Okay. The other way you could have gone about it is saying, I am just going to write out what my h inverse function is. I know that for inverse functions, you take the operations that you have acting on x here, and you do the inverse operations in the reverse order, meaning that multiplying by half or dividing by 2 is happening first. I want to do that last. Where here, what's happening last, x is a minus 3, I'm going to do its inverse operation first. So that means we're going to add 3 first. And then instead of dividing by 2, we're going to take all of that, the quantity of that, because we've already had that done, and multiply it by 2, and that gives us the same thing. If we simplify, we get 2x plus 6. Then they want you to find h inverse of h of 10. Well, one, I'm just going to do the brute force calculation, see what happens. If I plug 10 in for h, I'd have, notationally, I don't like, I'm just going to write what's h of 10 first. Okay, so if I do h of 10, this would be 1/2 times 10 minus 3, which would be 5 minus 3, which is 2. Now I'm going to take 2 and plug it in for h inverse, because note, h of 10 equals 2, so h of 10 now equals 2. Again, that output of the h is now the input for h inverse, 2. Now I have 2 times 2 plus 6 is equal to 10. Look at that. Same as the input. And that was something that we learned, important to note, that when you insert an inverse into the other function, your output is always going to be x. It doesn't matter if this is an x or a 10 or a 15. If we have h and h inverse, doesn't matter the order, your answer, no matter what the function will always be that input. Okay, determine if the function is 1-to-1. So what you want to do is 1-to-1, probably the easiest way to determine 1-to-1 is a horizontal line test, because if a function passes the horizontal line test, we're assuming it's passing the vertical line test. So ultimately what you're doing is determining if it passes the vertical and horizontal line test. And if it does, then the function is 1-to-1, because each input has exactly one output and each output has exactly one input. So if I look at this, I have a quadratic. I know if I graph the quadratic, it's got that negative out front. It's going to look something like that. It will not pass the horizontal line test, so that would be a no. A cubic function, you could just graph that, but we do know a cubic function, it got moved up 11 and flipped over, so it's going to look something like that. And that, if you look, will pass the horizontal and vertical line test, so that's a yes. Lastly, a line inverted graphically would also give you a line. Furthermore, you could also go like, oh, if I flip the x and y's and then solved, I get a line, which is a function. Furthermore, you could look at vertical and horizontal line test, and it would pass for both the vertical and horizontal. So yes, a line is 1-to-1.